And welcome back. So in this video, we're going to go ahead and introduce our value references, which are going to be used for our move semantics. Before we begin, though, I want to, as I've kind of alluded to earlier, I want to go ahead and acknowledge now and perhaps provide a bit more of a definition is the dual meaning of some sort of type name followed by ampersand, ampersand. One meaning is going to be an R value reference, which only binds to R values, with the primary use to identify objects that may be moved. So this you might see as maybe, okay, here's an R value reference to an integer object. And we'll get into what an R value is in the next slide, so hang tight. The other meaning of, say, some sort of type name followed by ampersand ampersand is going to be the universal reference, which can mean either an R value reference or an L value reference. This kind of dual nature of the universal reference allows it to bind both R values and L values alike. And you'll frequently see this as something like auto ampersand ampersand with auto type deduction followed by the declarator operator. Ampersand ampersand is going to allow whatever named this reference as to accept both R value references, to bind to either an R value reference or an L value reference. We're going to focus on the meaning of one, so R value references today, though kind of the idea expressed in number 2 is intriguing. So L values and R values. An L value represents an object that occupies an identifiable location in memory that lives beyond an expression. So if we go ahead and look at the example here on the right, we can see that I is an integer. I is a name for an integer object initialized with 0. And then we see the statement I is equal to 4. An assignment expects an L value as its left operand. I is an L value because it is an object with an identifiable location in memory. Now let's go ahead and contrast this with an R value. A R value is defined by exclusion, by saying that every expression is either an L value or an R value, and that an R value is not an L value. The easiest way to kind of think about this is an R value is going to be typically associated with temporary objects. So let's go ahead and look at the example on the right for the R value case, which is actually going to result in an error. So if we go ahead and initialize I with 0, and then let's attempt to assign the integer value of 1 to I mod 2. The expression I mod 2 produces an R value in temporary objects, storing the result of that expression. The resulting R value does not live beyond the expression that produced it. So it's there and then it's gone, kind of in a flash. And also it does not identify kind of a memory location where we could actually go ahead and go in and make this assignment too. So in this case, you'd see some sort of compilation error complaining that on the left-hand side of an assignment expression, there's an R value and that, well, this is going to be a compiler error and we'll have to go ahead and correct that to an L value because when we're making an assignment, again, you need to have some sort of identifiable memory location where you can go ahead and put the object or the value into that object. So L values and R values, one of the main differences between L values and R values is that L values can be modified because again, they're associated with some sort of identifiable region in memory, whereas R values are kind of associated with the temporary location that again is the value is gone at the end of kind of the line in which they present. So C++ has introduced the ability, though, in special circumstances, to have a reference to an R value and actually modify that R value, which is going to have some interesting implications because if you think about it, sometimes we have our functions returning something like that, a temporary object. I mean, we're kind of returning a return value optimization by the compilers right now, but there's a lot of times where kind of temporary objects are scattered throughout. So for instance, our doubly linked list type. say it's subints. Let's say it's DLL. Let's go ahead and initialize it with say int. This is going to call the the default constructor, and it's going to result in a temporary object on the right-hand side of the equal sign, which will then be used to initialize that on the left-hand side. So in C++, these temporary objects are kind of scattered all over the place. And the cool thing about R value references is that, let me just back this up. In this case, we just created kind of a linked list there. Imagine if it had memory associated with it. So maybe we're initializing DLL with a doubly linked list returned by a function. In that case, we'd have this temporary object returned, and then the copy constructor would be invoked to perform the initialization. That's done kind of here. So if we come up with some way to get around that with simply taking the resources from that temporary object, associating them with the persistent object, this process is going to be a lot faster because we don't need to perform an expensive copy. So with that, let's go ahead and move on and consider, I guess, what I was kind of alluded to right now, object ownership. And then we'll talk about kind of transferring ownership of resources explicitly using the standard library move function. And that move function is going to cast some sort of object to a R value. And then what's going to happen is we'll be able to use our move constructors and move assignment operator to actually invoke that transfer opposed to a copy.